Good afternoon, everyone, and welcome to this webinar on scaffolding design with SCIA Engineer. Today, I would like to tell you something about scaffolds and how to model and design them with our software SCIA Engineer. My name is Bjorn van den Steendam, and I work as Customer Success Team Lead at Allplan. During the presentation, the attendee audio is muted. You can use the questions box to ask questions during the presentation. After my presentation, I will have a look at the questions and try to provide an answer to them. This webinar will be recorded and posted on the SCIA by Allplan YouTube channel within a few days. In this webinar, we will discuss a small scaffold, as you can see on the right side. It's a simple scaffold, but it will allow us to indicate the principles on the scaffolding modeling, loading, calculation, and design. First, I will tell you something about the modeling of the scaffold. You can do it element by element, or you can make use of some tools, like some import tools. After that, we will create some load cases, apply the loads, and combine them into load combinations. Then we will run the analysis. First, we can run a linear analysis to have a look at some basic results. But for our scaffolds, we will need more advanced analysis, so we can proceed with stability analysis, which will indicate the buckling shapes. And finally, we can also run a nonlinear analysis with second order effects and imperfections included. After the analysis, we can run the scaffolding checks. There are specific checks implemented according to the scaffold code. And finally, we can create a report via our engineering report tool inside the software. Let's start with the modeling. For those who know SCIA Engineer already, you know that you can model it element by element. And there are some tools available in order to help you to model that efficiently and in a fast way. One of the tools is a line grid. We have 2D and 3D line grids available. A 2D line grid is simply a horizontal line grid, while with a 3D line grid, we also added the vertical component. And the advantage of a 3D line grid is that you can automatically generate drawings based on the grid. We also have some 1D member types available. We have the beam type, which allows you to insert a horizontal element. We have the column type for the vertical elements, and we have the 1D member itself, which allows you to define a member by the beginning and the end point. On the right side, you see as well the cross sections that we will use in this model. So we have an extensive library with all kinds of cross sections like IPE, HE sections, tubes, and so on. And you also have possibilities to add specific cross sections via a general cross section. We have parameterized cross sections and so on. And in order to assist you in quickly modeling the structure, we have all kinds of commands, such as a copying command, multi-copy, mirror, move, and so on. Another possibility to model something in a repetitive way is to make use of user blocks. Here you see an example of a lattice beam. So you model a part of the structure once, and you save that file somewhere on your hard drive. And then you can load that file into another project. And in that way, you can reuse something that you modeled once into any number of new projects. The location of that file is defined in the global UI settings. So there you can see we have, in this case, a user block library, and you will see where this directory is located. It's also possible when you don't have any file or project opened in SCIA Engineer to change that directory if you want to. Another tool is the input table, which you can see here. In the input table, we have the data of the model in a tabulated format. So for example, here you see a table of the nodes in a model, where you see the name of the node, the coordinates, so X, Y, Z, also the members that are linked to that node, and so on. And the input table has some advantages. They can be linked to Excel, so you can copy paste parts of the full input table to Excel, modify it, and copy paste it back to SCIA Engineer. In SCIA Engineer itself, you can also manipulate data in a fast way. For example, you can rename entities. Imagine that you model a part of the structure, you delete some elements, you model new elements. In that way, your order and your numbering of the elements and the entities can have gaps. So you can jump from node N25 immediately to node 54. The renaming command allows you to rename it properly and have a nice numbering again. It's also possible to round coordinates. For example, when you import from an IFC file, you often have a lot of decimals, which can cause inaccuracies during the modeling, during the connecting of your structure, and thus during the analysis as well. And with the rounding command, you can immediately, after the import, round your coordinates, for example, to 1 millimeter to avoid those kind of issues. Another option is to use mathematical operations. For example, you can select a number of loads and you can immediately multiply it with a certain coefficient. For example, when you have to change the class of your scaffold, you can immediately do an operation to change the loads in that way. There are also some import possibilities. One of the possibilities is importing from a DWG or DXF file. In that way, it's possible to immediately import a part or the full structure that is already modeled. So that will save you quite some time. It is recommended to use your system lines or your access lines of the structure, because if you connect those already properly in the nodes, you will already have a model, an analytical model that can be used and that you could immediately use for calculation of the model. It is advised, or it is useful, to work with layers already in the CAD software if possible, because in that way you can go a step further. You can not only import the lines of that file, but you could already convert them automatically to 1D members, so to SCIA, native SCIA Engineer members. If you do that with layers, you can do it layer by layer. So you can start, for example, with the columns. You can link them to your cross-section of the column. You import them and you do the routine again for the ledgers, for the guardrails, and so on. Other formats are from Revit and from Tekla structures. And a last one that I listed here is the IFC format. It's used from time to time, but keep in mind that IFC format is using the structural model, so not the analytical model. So after the import, the structure will not be connected yet, due to the difference between a structural and an analytical model. So you need to connect to align your members with each other, and therefore you could use the BIM toolbox in the software, but that's is a process that can take some time. So if you have already an analytical model, for example, via one of the other import possibilities, that could have the preference. After modeling the structure itself, everything will be connected rigidly by default. So if you want to apply certain stiffnesses or nonlinearity behaviors, you need to define it, for example, with a hinge. And you can assign to your hinges scaffold couplers. In our library, we have some manufacturer couplers, such as Cuplock, 3 of the layer types, and the Qatari type, which is coming from the US market. In the hinge type library here on the right side, it looks like this. So you see that we have 6 degrees of freedom, which you can define: rigid, free, flexible, nonlinear. With the manufacturer couplers, everything is already predefined and loaded from the library. And at the bottom, you can see the 6 resistance values. So everything is already prepared and set up. You only need to make a choice of the coupler type, and then it can be assigned. And on the left image, you can see some of the nonlinear functions that are automatically linked to one of the boundary conditions, one of the degrees of freedom. These are coming from the documentation, so for example, from the Zulassung of Cuplock and Lier. We also implemented some couplers which are coming from the Scaffold code. One of the types that is often used is the right angle type. You also see the friction sleeve, the swivel, and some other. Keep in mind that in the code, they only mention certain degrees of freedom. The other degrees of freedom we have put as 3, so that means that they don't have any stiffness, and that can give issues in the analysis. So if you have a load which could cause a certain force or moment in a certain degree of freedom, and in your hinge that degree of freedom is defined as 3, that can give an instability or issues with convergence of the analysis. And in that case, maybe you need some kind of stiffness in that component. It's also possible to customize couplers. So in case that you have a coupler which is not in our library, you can use the hinge type general and define every degree of freedom by yourself. Also possible to add the nonlinear functions. On our website, we have an Excel tool which can help with that to quickly import the data for that nonlinear function into the software. And of course, you need to define also the resistance values in that library item so that those can be used for your coupler check. You can also request an expansion of our library. In that way, you need to send the information of your coupler to our support team, and then they can create a request for it to the product team. So hopefully in a future version, your coupler could be available in the library as well. Of course, we also need to add some supports to the model. We can use the support in node command for that in order to enter some nonlinear friction supports, for example, or some anchors in case that you have a facade scaffold. You can use some anchors, so some rigid constraint for the X and the Y direction in this case. And then your structure is fixed or supported as you need to. Then something specific about the diagonals. If we make use of the Lier system, you will see in their Zulassung that they mention something about the stiffness of the diagonals. They also provide some tables for that. And with that information, you can derive a nonlinear function to apply here in this case for the UX component of the hinge on the diagonal. On the website as well, you can find a library which can be downloaded, which contains all the nonlinear functions for the diagonals of the three layer types that you see here. And then we can go to the software. So I already prepared a small model with some settings. In the project data, I activated steel and the Eurocode. In the functionalities, we have the stability functionality, non-linearities, such as the imperfections that we will define later on, the geometrical non-linearity, this is a second order effect, friction supports, and then under steel you can find scaffolding. If you don't activate scaffolding, you will not have the specific scaffolding checks available, and you will also not have the hinge type library with the couplers available. I have some cross sections defined. Some are from the library, the profile library with tubes and eye sections and so on. And I assigned a material for some cross sections. I used a material with an increased yield strength according the leerzulassung. I also created some layers that I can use to assign my 1D members to. And then we can start modeling. I will first create a 3D line grid with some dimensions, two spans of 2.5 meters, one of 2 meters, and again 2 of 2.5. The other direction, two spans of 1 meter, and then in vertical direction 5 times 2 meter, and my final vertical block of 1 meter. I insert it in the origin, and then I can start using 1D members. I can use the Alt right mouse click button to have that menu available. That's the marking menu, and I select a column element. The type is already chosen and set to column with a priority of 100. The type is important for your coupler checks, because in the coupler check you will have an interaction check, and for the interaction check the software needs to know which element is a column, which element is a beam, which element is a diagonal. Length, in this case a height of 2 meters, and I will add some columns in the first level like this. Then I can add some 1D members. I will model the beams, and I will define them with a beginning point and an end point. I will model those 4. And then I can right click, copy them to the other spans. You will see the middle span has a different dimension. So what I can do is simply model the beams anyway, copy them, and adapt, drag and drop the nodes to the desired position. Then I do the same for my transverse direction. Oh, this was too fast. Yeah, like this. Right click and copy again. With the enter button I could do the last command, but that was a copy. So I need the 1D member again. And now I will model my diagonals, my bracings. something like this. Oh, well, I have one. This is wrong. So let's correct it. I can select one, right click on the property and expand selection. So that's a quick way of selecting entities, also deselecting if you would like. And we could add an eccentricity to them. If we now look to the top view and we activate the volumes, you can see on which side the eccentricity is applied. If we want to have it on the outer side, we use a minus symbol and we have them where we want to. Now you can also correct or check yourself. If we right click and go to the view settings, we can display the structure with the color by cross section, and so we can check if the correct cross sections are linked to the correct members. Then I can copy a part of the structure. Let's copy it a few times. And then maybe as well in the front plane, like this. Also like this. Maybe some diagonals to go from the front to the back. Alright. What do I miss? I still miss my guardrails. So let's take a few of the ledgers and we can copy those. Let's copy from this point, and I want to have a point at a half a meter, so I can activate points on line every half a meter, which allows me to copy 2 times, and afterwards I can change the settings. These will be guardrails with the appropriate cross section, and you will see visually also that they have the correct cross section in this case. You can select, I will copy it to the other levels. This is not correct, so I will undo it. At a certain moment, if you have too many snapping points, it's easy to misclick, so you can deactivate them if you don't need them at a certain moment. And then you have less chance of making mistakes. And also here I can add a level. I can add some guardrails here with a copy them to the back, and then I can copy maybe that column, change the length to 1 meter, and copy them to some other positions. So in a few minutes we already have most of the structure. What we are still missing are the floorboards, so we can also start from the ledgers and create a copy. Now I need a new point. It's again the points on line 0 to 5, and I will copy them also to the middle and to the same dimension from the other side. Now I can go to the top view, select them, and also change the properties. So these will be floorboards, cross-section floorboards, and we need to rotate them. Always use the LCS rotation, because then Also, your principal axes are rotated together with the element. With the alpha rotation, your principal axis will not be rotated. So that's normally not what you want to. I can select my floorboards again and also copy those to the other levels. Again, deactivate the snapping points. Like this. And that should be it. Now the other possibilities, this is modeling by element and with the tools of the software. We also have some import tools. We can import from Revit, Tekla, IFC. In case of the IFC, you will need to align with the BIM toolbox. And with a file, you can also import from DWG. Let's have a look at that. I will go to my folder. There I have an example. This is a warning that you have quite some entities. In that case, nothing is selected, but I can use the tick boxes. So this is the same structure, but I have it with the center lines. And they are also nicely grouped in layers. So that's a plus, because if you do that up front, the software can recognize the layers from the CAD software, and we could directly import them as native 1D members. So let's do that. Let's start with disable and start with the columns. Import. We can directly define the properties of the lines that we want to import and convert. And then you choose an insertion point. And you see these are SCIA Engineer objects. And in that way, you can do that routine a few times. Next time you do the layers, then the bracings and so on. Each time you take the same insertion point, and in that way, in a few clicks, you have the full structure already, not only the lines, but already the SCIA objects, and you can proceed. So that can really save you some time if you have the model already. I also mentioned the input panel. So under tools, you can find here the input table. Oh, there it is. And in the input table, you have quite some entities available, nodes, 1D members, later on the supports. You can switch the workstation to the loads, and there you can make changes. For example, if you right click here in the multi-edit box, you have the possibilities available: rounding, coordinates, replacing, so that's for renaming entities, multiplying, for example, with the loads, multiply with a coefficient, and so on. Here you have some additional options as well. So that can be useful from time to time, for example, when you import from an IFC file. Then let's proceed with the boundary conditions. So let's go to our supports. I can right click on the Z equal to 0 property to select all my nodes at the bottom at once. With the marking menu, I can use the support in nodes. And let's start with the friction supports at the bottom. I define a big stiffness. 10,000 is the default value for both directions. The mu is the friction coefficient. So I put it to 0.5. So that's for my supports at the bottom. And then if it's a facade scaffold, I can anchor it to the building. So I can take some nodes at the back side of my structure and add a support with the X and the Y rigid and the other degrees of freedom 3. Something like this. Of course, you could also model a small beam to the back of the structure, and then you will have a crossing between the beam and the column, and therefore you can use what we call crosslinks in the software and assign, for example, a right angle coupler, and the end of the tube there you can put then the support, the anchor. Talking about the couplers, we don't have added any hinges or couplers yet. So let's go to the library, structure, and then the hinge types. I will copy all the available ones to our projects so we can have a look at them. So these are the ones from the scaffold code. So the right angle, you can see all degrees of freedom are defined. For example, the swivel, you will see that quite some degrees of freedom are set to free without resistance. So that could cause issues in your model if you would have forces or moments in a certain degree of freedom and they are free in your model, then you could have an instability or a problem with the convergence of the model. So keep an eye on that. These are the manufacturer couplers. So for example, the layer variant, and you will see that automatically all values are defined. Some stiffness is defined. Here you have a nonlinear function, which is loaded automatically. Also there, keep an eye on the function. Here you will see it looks horizontal, but there is in fact a small stiffness which is needed for the stability of your analysis. In older SCIA versions, this was a lower value, but when tolerances in the solver change, that could cause issues. So therefore, this value is a bit higher in the more recent versions. And then here you will find that general type where you need to define everything yourself, all degrees of freedom and all the resistance values. Well, we can work with the variant type, and then we can add a hinge on 1D and define from the library the variant on both sides. And you add it, for example, to your guardrails. So what you could do is quickly select everything you need. For example, I will select here, this one, the ledgers, right click, expand selection. I also take a guardrail. Now I have a mixed selection, right click on the guardrails, expand selection. So I have everything I need. The hinges, okay, that's fine. I had already 3 hinges defined, so I cannot create duplicates, of course, and I have all my hinges available. You could also add some boundary conditions to the floorboards, of course. Add some stiffness in the rotation, for example. What I want to show you as well are the diagonals. So we mentioned that for Liar they had specific guidelines in their Zulassung. So what you could do here is work with a hinge as well. So let's take maybe these diagonals with this length. I have immediately all the ones with the same length. I add a hinge. And now I will take it not from the library, but standard. Here I will create a nonlinear function. This can be a default value. That's only for the linear analysis. And then I can go to the nonlinear functions. And if you download them from the website, you can read them from that file that you will download then. I have them here on my computer somewhere. This is the list of that K2000 library that I downloaded. I go to a height of 2 meters, and I have these 3 types in my project, and I can assign the appropriate one to the correct length of the diagonals. And all the other ones I can put rigid, VY free, and then rigid again. And then you will see the hinges added to the diagonals. So this you can do for all the diagonals, but let's go back to the PowerPoint. You know now the principles. Let's have a look at the loading of our structure. So let's start with the load cases. We can define permanent loads, so that will be our self-weight. That can include other components. Maybe you want to add load of the toe boards, but you didn't model them, so then they can be added as a permanent load. Of course, the variable load, where we will make a distinction between the surface loads, wind loads, snow loads, ice loads, if required, of course. And you could also consider accidental loads, but in the analysis models, they are almost never considered. Probably they are already okay when you would consider them, but I rarely see them in the models. So these could be the loads that we can use in our model: self-weight, other permanent, surface loads for working wind and maximal wind, and then maximal wind in X and Y direction and working wind in X and Y direction. So let's have a look at them in detail. The surface loads, this is a table from the Scaffold code where they mention values for the loads depending on the load class. And then for the wind loads, we will consider a maximum wind load according to the Eurocode, and then a working wind load derived from a uniformly distributed pressure of 0.2. And then if needed, snow and ice loads. And for the combinations, we can consider two situations: the service condition, where we will combine self-weight and other permanent, of course, with Q1 on the working deck, the most unfavorable working deck, 50% of that load on the level above or below that most unfavorable one. So for example, here I put -2 on the top deck and -1 on the deck below. Also then the working load, or the working wind, sorry. And then the out of service condition, same for the permanent one. For the service load, we take a percentage of Q1 depending on your class. So in this case, if we would have a class 2 or 3, we take 25%. So that would be 1/4 of the 2, the value of 2. So we have 0.5. Only on one level. And then we combine it with the maximum wind loads. And we will create combinations for ULS, so ultimate limit state, with coefficient of 1.5, and serviceability limit state as a SLS state with factors of 1. And you will see here the combinations in this screenshot, where you can see that for the permanent loads, we have used a value of 1.2. This is something that comes from the Benelux, where they agreed in the scaffold industry to take 1.2 for the permanent loads. If we switch back to the model, I will disable some model data. I will show you just some principles, and then I will go to the full model. What you can do first is create load panels, because with a load panel, you can create surface loads. We'll just create a panel here on the edge to illustrate, like this. So this is a fictive 2D member, you could say, on which you can add a surface load, and the load panel will redistribute that surface load to 1D members. So it will generate line loads on your 1D members. So that's the advantage that you have with a load panel. And you can do it all around your structure. You can create another load panel here on your top deck, and there you can switch the direction to your Y direction, and then you will load the toe boards and the floorboards, and the floorboards will redistribute the loads to the short ledgers and so on. You can play with the transfer method. The tributary area is using the geometry of your structure, so it divides your structure in areas. With the accurate methods, a finite element mesh is generated and the stiffness of the structure is used. So that's a bit more accurate. Tributary area is a bit more easy to understand where the areas and the loads are coming from. You can also make a selection of entities. For example, in this case, you could create a user selection and update the beams because you probably don't want to load the outer ledgers and only the three floorboards in the middle. And then if you compare, you will see the difference between the row next to it. So here, this is the area that will go to the first floorboard, while here you have a part that goes to the edge beam or the edge ledger, and then a part to the floorboard. All right, so let's maybe open the full model to continue. Otherwise, we will lose a bit too much time. It's exactly the same model that we did together. What did we define for the loads? We went to the load cases. Or maybe switch here. Yeah, that's more easy. Load cases. So here I created the self weight, which is created automatically. You can see it here. The type is self weight, and we use the vertical Z direction. Other permanent loads could be the weight of your toe boards, for example. Service load in work, max winds, then the max winds and the working winds. What did we define? Let's maybe activate everything. You will see here that I created a few load panels. I have permanent loads. Let's see if I created something. Yes, I have here line forces. That are the toe boards. I have added them. If I change the scale a bit, you will see that they are applied to the ledgers. Then I created a service load in work. So that's my -2 on the top deck, half of it on the deck below. The service load with maximal wind, that was the 25% of my service load, only on the top deck. Maximum wind in X direction, maximum wind in Y direction. Here I immediately used line forces instead of the service load. It's another approach, both are valid. The working wind in X and in Y. And then I made the combinations. These are the linear ones. And you will see that I didn't create linear combinations yet. Why is that? Because my linear analysis doesn't interest me that much. So you could immediately create your combinations here in the nonlinear combinations dialog. And you will see the ones that I mentioned in my slides. So 1.2 on the permanent, 1.5 on the variable, and you will see this will be my combination out of service. So with the maximal wind and the service load with maximal wind for the Y direction. And then the service load, so that's the biggest service load with a smaller wind, with the working wind, 2 directions, and then the same combinations for the serviceability limit states. The bow imperfections I will explain just in a moment, so we will not focus on those yet. So let's have a look at the analysis types in our slides. Let's start with the linear analysis. So the linear analysis can be a first stability check of the structure. It can give an indication if your structure is connected properly, if the deformations are more or less acceptable, to get an idea of reaction forces. But a second order analysis with imperfections is mandatory according to the Scaffold code. This is mentioned in the table that is coming from that code. What kind of results can we have a look at? 3D deformations, reactions, also internal forces, and bill of material. I will demonstrate it in the software as well, of course. And then you can run a stability analysis. The stability analysis will learn you something about how the structure behaves. For example, how it will buckle. Here on the right side, you can see a buckle mode at the bottom columns of the structure. So in our model, we will run a nonlinear stability analysis because we have a model with a lot of nonlinearities in the model. The friction supports are nonlinearities. The hinges or couplers have nonlinear functions. So we need a nonlinear stability analysis to take that into account. What will a nonlinear stability analysis do? It will run first a nonlinear analysis, and it will increase the load until your structure becomes unstable. And at that moment, so the nonlinearities are taken into account, the software will go one step further, one step back, just before the structure became unstable. And on that state, that deformed state of the structure, a linear stability analysis will be executed. So it's a two-step analysis. The result of the analysis is alpha critical, so that will indicate with which coefficient your load should be multiplied for the buckle mode to occur. And of course, it will also give you the buckle mode or the buckling shape of the structure, as you can see here. And then in the last step of the analysis, you can run a second order analysis. You can define imperfections. One way is to define global frame imperfections. So that's what we also call the sway imperfection in the Eurocode. On the left image, you can see the image coming and the formulas coming from Eurocode 3. And you can combine it with a local or a bow imperfection. And that's the table that you can see on the right image. Or you can skip that and you can use the real behavior of your structure. And in that case, you can apply the buckling shape as an imperfection. When you have defined the imperfections, you can run the nonlinear analysis. And when you activate the functionality of the geometrical nonlinearity, you take into account second order effects. And important to know is that the geometrically nonlinear analysis respects always the conditions of equilibrium on a deformed structure. In the solver settings, you can find quite some settings for the nonlinear analysis. You see them here in the red square. You will see geometrical nonlinearity. We have here third order, which is in fact a second order analysis with increments. So it's also a second order analysis, but instead of putting the load immediately at 100% on your structure, you divide it in a certain number of increments. In this case, default setting is 5, so you will add first 20% of the load. You will calculate, or the solver will calculate. It will search for convergence. If it finds convergence, it will go to the next 20%, and so on until you have loaded the structure with 100% of the loads. And in the formula at the bottom, you will see what the convergence criterion is. So you have a left side and a right side. On the right side, you see 0.005 divided by the precision ratio, and that precision ratio is one of the parameters in the nonlinearity solver settings. So by default, it's set to 1. But in case that you want to have less precision, you could lower it, for example, to 0.1. So in that case, your structure will find convergence more easily. And that's a bit sometimes playing with the settings. By default, I would just keep it to 1, also the robustness ratio. But in case that you have difficulties with convergence, then you could try to play with it. For example, increase the number of increments so you have smaller steps, and that could have a beneficial effect on the analysis. You can increase the maximum number of iterations, so the solver gets more iterations to find convergence. You could lower the precision ratio a bit, for example, to 0.1, and you could increase the solver robustness ratio, for example, from 1 to 5. Always, when you obtain results afterwards, evaluate the results carefully. If you see strange reaction forces or deformations, check if it's realistic or not. Because if you play too much with the settings, like with the precision ratio, if you would really lower it to 0.01, 001, then you don't have an accurate solution anymore, and then your results will be unreliable. So that's for later. Let's go back to the software. In my model, I already have results. It's not grayed out, so I have results available. 3D deformations, and you can see if I have run the linear analysis, I can have a look at deformations. I see 8 millimeters, so that could be realistic. They also seem logic, so this could be okay. Reaction forces, we'll also stick to the cell weight RZ, so that's the vertical reaction force. Okay, it also looks quite okay. I think I forgot one support in that model. So you can quickly see that you made a mistake. You can correct it, of course. And here in the table, you can get the reports preview with a nice table that you can also send to the engineering report. And the number of values are defined by the extreme. So if I switch to global, I only will see the global results, so the minimum and the maximum for each parameter, and also graphically you will see the change. You can always also ask for internal forces, so normal forces, bending moments, and so on. And you can also ask for the bill of material. If I refresh, open the preview, you can have a small table with only the overall value, or you can go to a lower level, for example, to the 1D members, and then you get to see a nice table. Let's make it a bit bigger, with every cross-section and also every length. So here for the columns, I have 10 columns of 1 meter, 60 columns of 2 meter, and so on. And this can also be shown in what we call the results table. It's a bit similar to the inputs table. You have exactly the same table as in the preview, but this one could be copy-pasted to Excel or to Word. Or here you can also directly export it. If you have Excel on your computer, it will open it automatically. So my other screen, like this. And that's the table. So that can be useful as well to get an idea of your material in the project. Then I mentioned the stability analysis. Therefore, I created nonlinear stability combinations. I don't have to create them again. I can simply take new from nonlinear combination. I select my 8 combinations. I press close, and I have immediately, I don't need these now, of course, those 8 converted combinations. And in the analysis, I then execute the nonlinear stability. I need to refine my 1D members. This is by default set to 1. I have to increase it. Otherwise, I cannot have any buckling shapes because I don't have intermediate points, so the buckling shape could occur. And in the solver settings, I have here settings for nonlinear stability, the solver and the number of buckle modes I want to calculate, and then some properties which are a bit similar to the nonlinear properties, because prior to the stability analysis, a nonlinear one is executed, also with a maximum of increments. If that maximum is reached and your analysis didn't become unstable yet, it will stop and take that state for the stability analysis. So those settings, yeah, you can play with. On our web help, you can find more information about those settings. And then after the analysis, you can have a look at two things. That's the 3D deformations. Now you will have nonlinear stability combinations available. We'll take the first one, and you will see that it's a buckling shape of that column. And the 11 value is the alpha critical value. So if I go here, for example, to my combination number 4, it's a stability mode of my top ledgers that are buckling a bit. All right. And then we go back to the nonlinear combinations. And there you can now define your imperfections. So what we have done here, we follow the Eurocode approach, if I'm correct, for the first 8 combinations. We applied a bow imperfection, and there we took a simple curvature, 1 divided by 200 as local imperfection. I believe that's a value that is mentioned in the Scaffold guidelines in the Netherlands. And then we can apply imperfections, global imperfections, and for those I have created some buckling shapes. You can use the formulas from the code. Then you can simply choose the Eurocode 3, and it will apply the formula with a basic value 1 divided by 200. You insert the height of the structure, 11 meters in this case, and the number of columns in that plane. So in this plane, it will be, I believe that we have 6 columns in total, but the first one and the last one will only take half of the load. So I would take 5 here. A lower value gives a higher angle, so it's on the safe side anyway. And for the y direction, we only have 2 columns, so I take 2. And then what you could do is use that function with that angle. You could do that in Excel, and you could calculate some kind of S shape because you have anchors in this case. This is only for a facade scaffold. If you have a freestanding scaffold, you can directly stick to these inclination functions. And that's why I have here created a few of them. So also an X and then a Y in 2 directions. One's positive, one's negative. For the X one, I didn't do that because it's symmetrical in the X direction. And I apply those. So here my X wind with an X imperfection, Y with a Y imperfection, and so on. And then I have duplicated my combinations, and I made a copy of them, and there I created 4 additional ones, 4 with the minus Y imperfection, and then the last 4 with an imperfection coming from the buckling curve. So I have created 4 global imperfection functions with my 4 stability modes for ULS in this case. And I took my first eigenshape, and then you can apply a deformation. How is this deformation calculated? It's coming from your buckling modes. So in this case, I took the dimension from here to here, It's around 12.36 meters, sorry, and I divided it by 200 if I'm correct, and that gives me 62 millimeters, which is the value that I inserted for that mode. Why did I have to calculate it? Because a buckling mode is a normalized mode. It doesn't have a physical meaning. It's just a way of presenting the mode, being able to visualize it. So I need to assign a specific physical value in order to apply it as an imperfection. And then I can calculate, so then I can execute my nonlinear analysis. I can go to the solver, nonlinearity, and these are the settings that I showed you earlier. So third order, not second order, because then you immediately apply the full load, which means that you cannot have the effect of your nonlinear functions, because you have a nonlinear function with different steps, and you cannot apply it properly with a second order analysis. And then in the results, I will not show those again. You can ask again for reactions, forces, and so on for your nonlinear analysis. What I can show you, maybe it's interesting to have a look at, are imperfections. So here the global imperfections can be visualized. So for example, that X imperfection is nicely, oh sorry, in this direction of course, is nicely the S shape that I applied, and you see the matching value as well. If I take the Y shape, it's in the other direction, and if I take, for example, that last one coming from the buckling mode, you will see the buckling mode with now a maximum value that I applied. All right, so let's go quickly to the checks. We're running out of time. Let's go back to the slides for the scaffolding checks. So with the scaffolding checks, let's start with the ULS check for the members. We have the ULS checks implemented according to the scaffold code and also extended with the DIN 4420, because the DIN 4420 also provides interaction checks, while the scaffold code doesn't mention all of them. So it's a bit extended with what we have there. It basically are section checks, because stability effects doesn't have to be considered. Buckling is included in the second order analysis with the imperfections, and we are working with tubes, so we don't have lateral torsional buckling effects. In the steel settings, you have a tick box that the checks are applied for the tubes for CHS sections. It's activated by default. And in the output, you will see a graphical output. A ULS check above 1 would be red, below 1 is green, and below 0.25 unity check would be gray. So here in this case, everything satisfies. And you also have the preview, the report preview. There you can choose between a brief output, a summary output, or detailed. Brief is only a small table with the overall result. Summary is one A4 page with some data, and detailed is the most extensive output. So the internal forces are given. If activated, the formulas are given, they are filled in with the values, and you get the final results. So quite transparent to follow the full check. Then we have the coupler checks. We have the couplers according to the scaffold code. So those are the ones that we saw earlier, the right angles and so on. You can see that for the right angle and the friction sleeve, the scaffold code mentions an interaction check. So we applied those as well, as you can see here. Note that for the general couplers, so those are the ones that you implement yourself, you cannot have interaction checks. because you cannot enter the formulas for it. For the manufacturer couplers, it's the same principle. We check the components where they are given by the manufacturer, and we also check in a lot of cases the interaction checks 1, 2, and 3. They are mentioned here. I will not go in detail, but we check the combined effects. We also check the interaction between the ledger and the diagonal. That's interaction 2. And we check the effect between the ledger and the column. So that's some kind of local punching effect. That's also checked. That's interaction check 3. And the output is similar, but now on connection level, you could say. So we have only values at the nodes where you have the hinge at the end of the beam. And we also have a detailed or a brief output. This is the brief output, only a table with the values available, the unity checks, or the detailed output, which automatically show the formulas as well. So here you will see the internal forces, the resistances, the individual checks, and also the interaction checks. And you can see an interaction check 3. It's quite extensive. So you see that there's a lot of formulas that are used to derive to that to come to that check. And last but not least, the SLS check. Typically, L divided by 100 is the limit for your SLS deflection check. You can define that limit in the steel settings or via the buckling groups. And as output, you will have both graphical output and table output. You will see here both. There's not an extensive or a detailed table output available because we only take the deformation, the relative deformation, that's important, from the finite element analysis, and we compare that one with the limit that you define in the steel settings or in the buckling groups. And then you have also the engineering report. With the engineering report, you can add all kind of data, tables of your nodes, of your members, of the load panels, the hinges, and so on, the cross-section characteristics, your loads with pictures you can customize with your logo, and so on. You have a 3D functionality for images, so when you export it to a PDF, then you can send the PDF to someone else, and he or she can have a look in 3D in that image if you activate that functionality. You can indent images so they generate pictures automatically, which is very useful, for example, with your load cases. You can generate drawings according to the 3D line grid. And very important and useful, save your project or your report as a template so it can be reused for other projects. So you don't need to make that structure of your report over and over again. I will very quickly show those last things in the software, but for example, for the engineering report, we also have already a nice webinar available on our channel, our YouTube channel, so you can have a look in detail if you want to learn more about that. So let's have a brief look in SCIA. I can go to the steel service, go to the ULS check for my members. I take the class with the nonlinear combinations, the ULS combinations. I refresh, and I have my unity checks available 0.74, so it satisfies. And then in the report preview, I can see this is the detailed outputs. There you can switch. You can switch with tables, formulas, or both. And then you see the internal forces, the table with the checks, and the formulas. Same principle for the coupler check. So also there I take the class with the ULS, detailed or brief. I refresh, you can see it's the unity checks at the end and the beginning of the beams, and the report preview again with 0.92 as well. The resistances coming from the library, the individual components that are checked, and then the 3 interaction checks as well. And then the SLS check. This takes the steel settings for the SLS deflection check, which are here. I have set 100. The default value is different. It's 250 or something and 360, so you need to change. The default value is just a fixed value. You need to override it. Or you work with buckling groups, where then you need to define the buckling settings per group of members. So you could do that via the 1D members. And then here you can define system lengths and buckling settings. And there you can override the steel settings. So that's possible as well. For buckling, it's not really relevant, but for the deflection, you can define it over there. Okay, and then you can execute that steel SLS check. Okay, now I lost the results, but the same principle applies, and you will get a graphical result and also the report preview. And then to end, I can go to the engineering report. I will open this one. Like this. And you will see I add a header, a page format, table of contents. They're all updated automatically, and you can modify. So if you take the header, you can edit it, you can change, you can delete a picture, add your own logo to customize it. Here I made a chapter with the model. So this is a picture where I can activate 3D export if I want to. Then a table with the nodes, with the members, and so on, with the supports. If you want to modify this one, it's also possible. So if you want to show the stiffness, for example, if I go over the X one and I want to add the stiffness and the friction coefficient, I can do it like that. And then like here with the load cases, I have a load case. I add a picture, that's this one, and then I have indented it. So if I now regenerate this item, you will see that now for each load case in my load cases table, a picture will be generated. So that's quite powerful. It can take some time, especially if you have a lot of load cases, of course. But you will see the effect just in a minute. There it is. Load case 2. That are my other permanent loads, the line loads that we saw earlier. Then the service load inward, the -2, -1, -0.5 with the maximum wind service loads, and so on. So that's quite nice, I believe. You can add the combinations with the coefficients, and then you can add a chapter with results, like with the buckling modes of your nonlinear stability, table with the reactions, your bill of materials. So all the stuff that we saw already in the software, you can add them as well then in your report. And you could end with gallery pictures. So if you create pictures with the picture wizard, you can also add those in the model. So for example, a picture like this. Afterwards, you can print a report to printer, physical one, or PDF creator, export to different formats. The 3D pictures should be exported to PDF, not printed to PDF. That will not work. And you can also save as a template. Then you give it a name, and it will be stored on a specific directory. And then afterwards, it should be visible here under report templates. You should have a new option, user templates, where you will find your stored templates. and you can simply add it to an empty report in another project, and then those items should be loaded, and when you regenerate, your picture will be updated according to your new project, same for your tables and so on. So this brings me to the end of this webinar. Thank you for joining, and I will have a look at the questions that came in and try to provide an answer to them.